Hello, welcome to another module in this massive open online course. So, we are looking at example problems in the Fourier transforms. Alright, so let us continue our discussion, and we have completed our discussion on the Hilbert transformer. Let us start looking at another interesting problem, that is to understand the process of filtering. Okay. So, we are looking at examples or practical examples for the Fourier transform. And in this particular module, let us understand the process of filtering. You will recall that we have discussed ideal filters, high pass, low pass, band pass and band stop. So, we are going to look at an application of the theory of filtering. Okay. So, now as you might already remember or recall, so let us term this as, so this is problem number 16. So, we have an ideal low pass filter. So, consider an ideal low pass filter, and in this ideal low pass filter, if you might remember, the ideal low pass filter response looks something like this. So, I have a cutoff frequency omega c, and the response magnitude of HF equals 1, or we can also call it h of omega instead of just magnitude. So, h of omega equals 1 for omega magnitude omega less than omega c, and h of omega equal to 0, otherwise this is an ideal low pass filter. Okay. So, this is your ideal LPF response, and this can be characterized as h of the response of the LTS system, h of omega equals 1 for magnitude of omega less than or equal to omega c, and this is 0 otherwise, or magnitude of omega greater than omega c, this is 0. Okay. Now, what we want to do is, for this LPF we want to consider an input signal. So, our input signal to the LPF input equals, the input signal equals x of t, given as the input is x of t equals e raised to minus twice t ut. This is our input signal. Now, what we want to do is we want to design a filter. So, this problem is with respect to filter design. So, we want to design a filter, which means we want to design or choose a cutoff frequency omega c such that it passes a certain fraction or a certain desired component of the signal. Now, what is that desired component of the signal? So, what we want to do is we want to find omega c of the low pass filter such that the filter passes exactly half of energy of the given input signal. Okay. So, the point is we want to find omega c such that the LPF, that is your ideal LPS, passes exactly half or allows exactly, there is the energy of the output signal should be half of the energy of the input signal, that is e raised to minus 2t ut. Okay. So, this is our design problem, filter design problem, and we can approach this problem as follows. Now, first let us use the Fourier transform approach. So, first note that we are given this signal x of t equals e raised to minus 2t ut, which implies now taking the Fourier transform, now x of omega of this signal is 1 over j omega plus 2. Now, therefore, we know from the theory of the Fourier transform that the output Fourier transform y omega is Fourier transform of the input signal x omega times Fourier transform of the filter response, that is h of omega. So, y omega is x of omega times h of omega, which is now, remember, h of omega is 1 only for magnitude of omega less than omega c. So, it allows only the signal component or the frequency components of the signal in this minus omega to omega c band to pass through, and it suppresses, because its response is 0 outside of this band. So, it suppresses all the frequency components which are outside this band. So, what we have is this is basically 1 over j omega over 2 for mod omega less than or equal to omega c, and this is 0, this is 0 otherwise. Now, the energy of the signal this is equal to, now first let us find the energy of the input signal, that is minus infinity to infinity magnitude x t square, minus infinity to infinity magnitude x t square dt, which is minus infinity to infinity e raised to, or 0 to infinity e raised to minus 4t dt, which is minus 1 by 4 e raised to minus 4t between the limits 0 to infinity, which evaluates to basically 1 over 4. This is the energy of the input signal. Now, we want to use the concept of what is known as the energy spectral density. Remember, energy spectral density gives us the distribution of energy of the input signal over the frequency spectrum. So, this is a very good example to illustrate the illustrate a practical application of this concept of energy spectral density. Okay. So, now what we want to do is we want to consider the ESD, or the energy spectral density of output. Now, remember, the energy spectral density of the output, that is magnitude y of omega square. Remember, we have seen what is y of omega, we get y of omega from this expression. So, magnitude y of omega square is basically 1 over 4 plus omega square for magnitude omega less than or equal to omega c and 0 otherwise. So, this is the energy spectral density of the output signal. So, this is your this is the ESD, the energy spectral density of the output signal. This is 1 over 4 plus omega square, correct, for omega, the frequencies that lie in the band omega c, minus omega c to plus omega c. Okay. And therefore, the energy of this output signal is nothing but the integral of the energy spectral density over the entire frequency band, that is from minus infinity to infinity, but it is only non-zero from minus omega c to omega c. Therefore, it is the integral of the energy spectral density from minus omega c to omega c. So, therefore, energy of output, now we have a very interesting application of the energy spectral density minus infinity to infinity, magnitude y of omega square d of omega, which is minus omega c to omega c. In fact, this is 1 over 2 pi, I have to have a factor of 1 over 2 pi, this is a constant factor, scaling factor, 1 over 2 pi times 1 over four plus omega square d omega which is minus omega c to omega c 1 over 4 into 1 plus omega square. Now, I am going to simplify this integral 1 plus omega square by 4 d omega. Now, if you look at this, this is nothing but 1 over 2 pi into 1 over 4 into tan inverse omega over 2 evaluated between the limits minus omega c to omega c times 2. So, this is basically you have 1 over 4 pi tan inverse or 1 over 4 pi 1 over 4 pi into twice tan inverse omega c by 2, which is equal to, now you can see this is 1 over 2 pi tan inverse omega by 2. So, this is the energy of output. You can also call this as E y, this is the energy of the output signal. This is 1 over 2 pi tan inverse omega c over 2. This is a function of, this is naturally going to be a function of the cutoff frequency omega c of the ideal low pass filter. Okay. And now, all we have to do is basically equate this to half of the input. So, we know that we want to design the filter with a cutoff frequency omega c such that the output energy is basically half of the input energy, and the input energy is 1 over 4. So, half of the input energy is 1 over 8. So, basically what we have is E y equals half of E x, which is input energy, which means 1 over 2 pi tan inverse omega c over 2, this is equal to half into 1 by 4, which implies basically tan inverse omega c by 2 equals pi by 4, which means omega c by 2 equals tan of pi by 4, which is 1, which means omega c equals 2 radians. So, that is 2 radians per second. Omega c equals 2 radians per second. So, that is basically, this gives us a filter. So, this gives us a filter such that the input energy, alright, such that the energy of the output signal corresponding to the input signal e raised to minus 2t ut, that is the exponential signal, the output energy is basically half the energy of the input signal. Okay. So, the cutoff frequency omega c is basically 2 radians per second. Okay. Alright. So, let us proceed to the next problem, that is problem number 17, and this is with respect to an RC filter, and this talks about the rise time of an RC filter Okay. And this deals with the concept of the rise time of an RC filter, and the problem is as follows. So, let us say we have a serial RC circuit we have a serial RC circuit, the output across the capacitor, the input is the signal xt and the output across the capacitor, the output voltage across the capacitor is yt. So, this is your serial RC circuit, and now the problem is to find the unit step response and explicitly find the rise time, that is the time that takes from the step response to go from 10% to 90% of its final value. Characterize the rise time. So, for a unit step response we have an output for this RC circuit. Okay. Now, what we want to do is we want to characterize the rise time. What is the relationship of the rise time? Specifically, what is the relationship of the rise time of this RC circuit? That is the time it takes to rise from 10% to 90% of the final value, alright, in terms of the 3 dB frequency of this RC circuit. Okay. So, that is what we want to do. So, we want to characterize the unit step response. So, we want to find the unit step response, that is the first step. And then we want to characterize the rise time. In terms of 3 dB. Now, rise time is basically time taken to go from 10% to 90%. So, time taken to go from for the time taken for the capacitor output to go from 10% to 90% of its final value, that is termed as the rise time of this serial RC circuit. Okay. So, now let us approach this problem. Now, we have seen this several times before, that is the input voltage xt is the voltage across the resistance, is the voltage across the capacitor plus the voltage across the resistance, which is I times R times I, but I is C dV by dt, where dV is the voltage across the capacitor. So, this is C dy by dt. This is the differential equation that, okay, this is basically differential equation for input slash output relation of RC circuit. Okay. And therefore, this implies that x of omega, now taking the Fourier transform, once you take the Fourier transform, we have x of omega equals y of omega plus R C dyt by dt has omega Fourier transform j omega y omega, because if the Fourier transform of yt is y omega, the Fourier transform of its derivative is j omega times y omega. Now, we have a simple equation in terms of the Fourier transforms which we can solve to obtain the transfer function. So, this implies that basically what we have is y omega divided by j omega, or y omega divided by x omega. This is basically 1 over 1 plus j omega R C. This is 1 over 1 plus j omega R C, Now, the unit step response can be found as follows. Now, remember this is equal to h of omega, this is the transfer function. This is the transfer function, okay. And now unit step response, now consider the unit step function ut which is equal to 1 t greater than equal to 0 and 0 otherwise. This is your unit step function, or this is your unit step signal, and if you take the Fourier transform of this u of omega, we already know this is pi of delta omega plus 1 over j omega, this is the unit step response, okay. And therefore, we have y omega, the output corresponding to the unit step response is basically the Fourier transform of the unit step response, that is u omega times the transfer function h omega, okay. That gives us the unit step response, that is the output of this system corresponding to the unit step input signal, okay. So, this is basically u of omega times h of omega, which is pi delta omega plus 1 over j omega times 1 over 1 plus j omega r c, which is now pi of delta omega into 1 plus j omega r c plus 1 over j omega into 1 plus j omega r c. And now look at this, pi of delta omega into 1 over 1 plus j omega r c. Now, we know pi of delta x into f of x is basically pi of delta x into f of 0, correct. So, similarly pi of delta omega into 1 over 1 plus j omega r c, this is simply, if you look at this is simply equal to pi of delta omega into 1 over 1 plus j omega r c evaluated at omega equal to 0, which is simply pi of delta omega. So, you look at this, you can convince yourself that this is the first term is simply pi of delta omega plus the second term, which is 1 over j omega into 1 over 1 plus j omega r c, which is pi of delta omega plus 1 over j omega minus 1 over j omega plus, now I can use the partial fraction expansion for this. So, what I am going to do is I am going to use the partial fraction expansion 1 over j omega into 1 over 1 plus j omega r c. So, I am using the partial fraction expansion for this. So, this is 1 over j omega minus r c over j omega plus r c, which is basically pi of delta omega plus 1 over j omega minus 1 over, now I will bring the r c in the numerator to the denominator, that will give me 1 plus j omega divided by r c, okay. Now, I can also write this quantity as 1 over 1 plus j omega divided by omega naught. I am going to explain this in a little bit. So, omega naught equals 1 over r 1 over j omega over this is j omega r c, j omega r c sorry, there seems to be some mistake. This is j omega RC, RC over RC over 1 plus j omega RC, 1 plus RC over 1 plus j omega RC, 1 over j omega plus 1 over RC j omega plus 1 over RC, okay, j omega plus 1 over RC. Okay, let me just keep this as it is for a moment. So, this is 1 over j omega plus 1 over RC. Now, what this is, now if you look at this, now if you take the inverse Fourier transform, now look at this, this is nothing but your signal, the unit step ut, this is pi delta omega plus 1 over j omega ut. Now, this is 1 over, this is of the form 1 over j omega plus a. So, the inverse Fourier transform of this is e raised to minus at ut, where a is this constant 1 over RC. Okay. So, the inverse Fourier transform of this is e raised to minus t over RC times ut, and therefore, the net taking the inverse Fourier transform. So, you take the inverse Fourier transform, and what you have is the output of it equals ut minus e raised to minus t over RC ut, which is 1 minus e raised to minus t over RC ut, e raised to minus t over RC ut. Okay, so, this is what we have. And if you plot it, it is going to look something like this, which is something you must have seen before. So, I have the time axis, this is the unit response, this is the unit step, the ut, and what happens is if you look at the response of the RC circuit, it starts from 0, it is 1 minus e raised to minus t over RC. So, at t equal to 0, this is 1 minus 1, that is 0, at t equal to infinity, this is e raised to minus t over RC, at t equal to infinity, e raised to minus t over RC is 0. So, 1 minus e raised to minus t over RC is 1. So, it starts from 0 and at t equal to infinity it approaches 1, and okay. So, this is basically your 1 minus e raised to minus t over RC into ut. Okay. So, and this is known as the time constant, this RC is known as the time constant. Larger the time constant implies slower the rise. Okay. If the time constant is larger, it means the rise is more sluggish. Okay. So, all these things I think are fairly large time constant. And so, large time constant implies slow rise, small time constant, so very small time constant implies fast rise. So, for a large time constant it implies very slow rise. Okay. So, the rise is very sluggish. Okay. All right. And all right. So, the time constant is, and now what we want to find is we want to find the rise time and find its relation to the 3 dB frequency. So, what we want to do is and we will do this in the next module, find rise time. So, we need to do two things, find the rise time to relation to the 3 dB frequency, okay, where f 3 dB, this is the find its relation to basically the 3 dB frequency. So, we want to find the rise time and find its relation to the 3 dB frequency of the circuit. Okay. All right. So, we will stop this module here and look at other aspects in the subsequent modules. Thank you very much.